Okay, so sorry for the delay. So we have something. Now this is the second talk. Our new pair is İrfan and
Hello, I am Salha, and this is my mentee İrfan. He's a mathematics student at METÜ. He worked on number theory and elliptic curves. Today he will tell us about elliptic curve cryptography. Before leaving the stage, as a classic, I would like to thank the organizers for the event, for making it possible, and for having us fun. Okay, thank you, then the stage is yours.
Hello everyone, I'm İrfan. Thank you, Salha, for fun summer. I'm going to talk about elliptic curve cryptography today. I'm going to first give a brief introduction to cryptography, talk about basic definitions of cryptography basic ideas, and then go into elliptic curves, give some basic facts about elliptic curves, and then I will examine cryptography aspects of elliptic curve, and then lastly I will show you an attack of ECDLP, curve cryptography problem. It's a hard problem for elliptic curve cryptography. As you know, the purpose of cryptography is to transmitting data with high security. In this process, most vulnerable part is sending part, so we always use encryption. The tool we use for encryption and decryption is called keys. Okay. There are two main methods for encryption. One is symmetric key cryptography and one is public key cryptography. Public key cryptography is like this. I have two keys, one for encryption and one for decryption. Encryption one is public, known for everybody, known by everybody, and decryption key is secret. Only I have this key. I gave encryption key to everybody, and if someone wants to send me a message, send me a plain text, he uses this encryption key to encrypt plain text, and to me, since only I have the decryption key, I am the only one. Which obtain plain text. And symmetric key cryptography is a little bit different. Only there's only one single key for me and for the second person, but it brings another problem with it. Key exchange problem. You have to exchange keys, and we want to do this securely. You can see an example there. For public key cryptography, encryption is easy. Everybody has encryption. But decryption is more harder without decryption. In this example, we use F19 as field, so it can easily be broken. Of course, to rate this situation, we use hard numbers, use large numbers, and forget about brute force. And let's see what elliptic curves is. Elliptic curves definition is the following. Let's say we have a field characteristic, 1, 2, or 3, and we have a cubic polynomial with no multiple roots. Elliptic curves is set of points which satisfies this equation, and we have to include one more element which is called point at infinity. Basically, serve us the role of identity. We actually can construct an abelian group structure on elliptic curves. we will see in a minute. As I said, we can construct a good structure on elliptic curve, but how do we do it? We need an operation. And we will define the operation as the following. If we want to add P to Q, then we draw a line from P to Q. And the line will intersect one more point at the curve. In this case, it's R. And we take the reflection of it. The point we get will be P plus Q. And we, if we want to add P to P, then we draw a tangent line to P. It will work perfectly well defined. Also, as a point at infinity is identity, and the order of the points is usual. Let's see the aspects of it. Okay, first we want to use finite fields because we want to do cryptography with computers. It is up for that. It has out for that. Let's start at cryptography problem. What is the cryptography problem? Well, in the beginning of the talk, I talked about key exchange problem. Actually, this cryptography problem is hardness of this problem is equivalent to security of key exchange process. If someone can solve this, then he can get. What is this problem? If we are given a point from FQ star and a point from the group generated by A, then finding key, where A2 key is equal to B, is the problem. And there's an elliptic curve cryptography problem. It is an analog of this problem. In there we have a point from elliptic curve and a point from the group generated by P. We are trying to find K, where K is K times P. It is harder than this cryptography problem, so we have to use this. Okay. Key exchange algorithm the security of key exchange algorithm and hardness of this cryptography problem is equivalent. But how is it equivalent? There's a key exchange algorithm. There's Alice, Bob, and there's another person. Alice and Bob try to exchange keys. They want to create a common key. They do it like this. First, they get an elliptic curve over FQ, and they choose a point B, which is publicly known. Then Alice and Bob will choose an integer that only they know. Then they multiply it with point B and obtain PA and PB. And then they exchange the points. At this point, PA and PB known by everybody. Third person also known. And then, since only Alice and Bob know their integers, they multiply it with PB and PA, and both can obtain PAB. But since third person doesn't know integer A and integer B, he can't get point PAB. Okay. Now I'm going to examine an attack. What does attack mean? It's an attempt to solving a problem, solving a problem, or simplifying it. But before getting into attack, I want to show you another concept. Let's say we have a point on E. and we want to add it to itself. And we can obtain a basic formula for NP. You can see there's three different functions, symbols. They are actually sequences, polynomial sequences. Two of them can be obtained by psi n, which is the only important sequence for us. It is square root of the denominator of x coordinates. You can see here. If it is evaluated at Pn, it is 0, then it means that P is 0. As you have to like this is 0, and they are infinity points. Okay, you can see here a more general explanation for psi n. You can use when index is odd this equation, and you can use if index is even and psi n has these two beautiful properties. First one, if n divides n, then psi m divides psi n. It comes from Lagrange theorem. And second property is a recursion property. Psi n also satisfies this. It doesn't really give some intuition or mean, but we can deduce from these two properties these two terms. First term helps us to carry this psi n in psi index to coefficient of p. So it should give us some intuition about relation between psi function and elliptic curve. And the second term helps us to reduce the index. Let's say order of point p is n. We can reduce n, and you can see can reduce n and multiply psi t with coefficient. With the help of these two theorems, we can see what our attack is. First, we need an assumption. The assumption is elliptic curve has q minus 1 point. The help of this assumption with algebraic manipulations, we can get this equation. You can see here these psi functions will give us elements of psi fq star. And I want to emphasize in the term in the middle, we don't know k. Actually, our purpose is to find k. So it's impossible to compute this, but we know it is an element of fq star. And we know the order of fq star, q minus 1, which divides q square minus 1. That implies that it's be 1, and we can avoid this and obtain a much more good result. Like q square p and this. Observe that this is actually a discrete logarithm problem, which is simpler than the discrete logarithm problem. So attack this, but I want to say one more thing. From elliptic curve equations, we can get this psi q term has only order 1 or order n. If its order is 1, then we lost the information of k. So as an attacker, we want it to be n. If the order is n, then our attack is successful. And the second theorem implies that this term has order n with high probability. Okay, this is my references. And
So, any questions? Yeah, so in the previous slide, you mentioned that the discrete logarithm